January 13, F322. This is a fairly standard starter question for you here. Crude oil contains many hydrocarbons, and they've given you a table, molecular formula, boiling point. The first question, what is the empirical formula of hexane? So you've got the molecular formula there of hexane. If it was more complicated than this and you weren't quite sure, take the carbon, divide it by 6, so you get C1, and then try the hydrogen. Can you divide them by 6? In this case you can't. Then you could go through, well, can I divide 6 by 3? 2. Okay, can I divide 14 by 3? No, I can't. So in this case, you've got the molecular formula, which is the simplest whole number ratio of C3H7. The next question then asks, explain why hexane is both saturated and a hydrocarbon. This has come up before. You need to learn these two, what are the definitions for saturated and for hydrocarbon. Here we've got then, first of all, saturated, it has carbon to carbon single bonds. The only here is not so important as in the next definition, but it has carbon to carbon single bonds only. Leave no doubt, that's all it's got. For the hydrocarbon then, this one, it contains hydrogen and carbon only, and you will not get the mark unless you put only, keyword. The next question up, draw the skeletal formula for 2,2-dimethylbutane. When you're looking at these, start by looking at the end words. So butane, how many carbons in butane? Okay, 4. Then methyl, so we're looking at a particular CH3 group, di meaning 2 of them, and then the numbers giving the position, both on carbon number 2. So here we've got 1, 2, 3, 4 carbons in a row for my butane, and then I've gone to carbon 2 and I've put 1, 2 carbons on. Next one, describe and explain the trend shown by the boiling points of the hydrocarbons in the table. So going back to the table here, we've got a situation where we've got hexane 69, we've got 3-methylpentane, same molecular formula with a slightly lower boiling point 63, and 2,2-dimethylbutane C6H14 still, but an even lower boiling point. So the first thing you need to do is state exactly what the trend is from the table. So we've got here, as branching increases, boiling point increases. And then we can say why branching reduces boiling point. Branched isomers have less surface contact. And then your final, for your third mark, your conclusion, what are the intermolecular forces? And you must state the particular intermolecular force we've got here. So weaker van der Waals forces. Now for part E, decane C10H22 is cracked to form hexane and one other product with and you've got to write a reaction equation for this. My suggestion here is always to use ethene. So I would go with CH, this is going to be interesting, isn't it? CH1022 goes to C2H4 plus C8H18. I'd always go with that one there because cracking, you can give the two uses. C2H4, which is ethene, is used for the manufacture of polymers, and C8H18 is octane, which is the key ingredient of petrol. So I'd always go for those two in that equation there. Make sure your presentation is clear, unlike mine. Now, in the presence of ultraviolet radiation, butane reacts with chlorine to form a large number of organic products. The key word here is ultraviolet radiation. That should be focusing in on a particular type of reaction mechanism. Several of these products are structural isomers of C4H8Cl2. Notice here as well that we've got this key part in this verse, F1. Write an equation using molecular formula for the formation of C4H8Cl2. Now, the classic error here for this one, what most people do here is write, okay, I've got C for what is C4H10 plus Cl2. It's going to give me, and this is the classic error, right, C4H8 Cl2 plus, well, what's left over? Yeah, may as well stick an H2 there. That's the classic error. That's when you've not picked up on the clue of UV radiation, that there are several products produced, a large number of organic products, but it does have molecular formula. I have used there the molecular formula, but that is incorrect. I'm going to take us down to a blank piece of page now before I'll rub that out, and let's have a bit of a more of a look at how we can answer this question. So sliding right down the page, and I'm going to go through this now because it's important for this bottom question as well here. Because this is going to help us complete the missing species in the propagation. Here we've got at the bottom, if we put in, and we do, actually I'm going to have enough room here, C4H10 plus just Cl2. And if we've recognized now that we've got propagation and UV light and we're doing a radical substitution, which is what this is, then we should get C4H9 Cl plus, all importantly, HCl. So that's my radical substitution equation. So if I'm going to go over again and I want to get C4H8 Cl2, I'm going to need to get two chlorines to react, and I will end up with 2 HCl. But let's just go through the propagation steps to check this is going to be correct. So in my propagation, that's the overall equation. Let's change color. In my propagation, I've got Cl plus C4H10, which is going to give me C4H9 radical plus HCl. So I get my HCl, then I bring my C4H9 radical down and I add it to Cl2. This gives me my Cl2 for the overall equation, and then I get C4H9 Cl plus a Cl radical. Now if I keep on going with this mechanism now, and I take my C4H9 to start with, so a different colour again, scoot down a bit, so that then I have, starting my second step, if you like, just get me back on pen, I'm going to have C4H9 Cl plus a Cl radical then gives C4H8 Cl radical plus HCl. Take my C4H8 Cl radical down, add it to C, go away, Cl2, and it will give me C4 when you get right into it, C4H8 Cl2 plus a Cl radical. Now if I cancel all this through, my radical here cancels. Let's change the colour. My radical there cancels. My radical here cancels with this one. So this radical cancels with this radical. Here we are, this radical cancelling with this radical with that radical. And in fact, we can cancel out, we've got C4H9Cl on both sides as well, from there and there. And then so I can give myself the overall equation which we were looking for, C4H10 plus 1, 2 Cl2s gives me C4H8 Cl2 here plus HCl and HCl plus 2 HCl. Apologies about that. Don't know where that red's come from. So that overall equation goes in there. So going back up to where the question was here, we then can have C4H10 plus, here's the red back, Cl2 goes to C4H8 Cl2, and notice that's molecular formula. I've got all the atoms and their numbers, I've not positioned anything, plus 2 HCl. What I've done is forget to put the 2 in here, because otherwise it doesn't balance. So you've got 4 chlorines, check that both sides, 4, and you've got 10 hydrogens, check that as well. Okay, that's where we are there. Now before I go on to do that one, while we're looking at this, down the bottom here, complete the missing species in the propagation steps below. We've done that here. So Cl plus C4H9Cl, we're going to get our C4H9 radical and HCl, and then further down, ooh, hang on a minute, no we're not, that's going to be a C8 radical, isn't it, with a Cl, HCl, sorry, I'm down here, aren't I? That's the bit I'm doing. So that's C4H8Cl plus HCl. That comes in again as the radical C4H8Cl plus the Cl2 gives me again my Cl radical and C4H8Cl2, which we had down here. So, getting back to the real question. Here we're asked to complete the table below about 2 of the structural isomers of C4H8Cl2. I've got 1,4-dichlorobutane. So it says complete the table below and show 2 of the structural isomers, but it's given you a clue of how it wants you to present the formula because it's given you a displayed formula here. So repeat what they've given you. Here then, if I'm going to fit it all in, Cl at the end, then 1, 2, 3, 4 carbons, and it's 1,4, so a Cl at the other end too. Then make sure you put on all your H's, so there is no doubt in the examiner's mind that you weren't accidentally going to put a chlorine anywhere else. So that's that one. Just check, I've got 1, 2, 3, 4, yeah. So that's 1,4-dichlorobutane, and here I've got a chlorine on number 1, 2, and on number 3. So this is 1, 3 dichlorobutane. So it's not until part G that they actually tell you that it's radical substitution. I suppose I've jumped around here a little bit. So it's telling you now that butane and chlorine is an example of radical substitution. It's been hinting about it all the way down. So you've got initially that C4H9Cl is formed, and then it forms C4H8Cl2. So if this wasn't your real exam, at this point, if you'd done something funny in that first equation, like that error I said that was often made, here you'd be seriously thinking about changing your mind if you came down to this question and saw that it was more about radical substitution. Now in this part 1, because obviously we've covered part 2 now, we've got to define homolytic fission. So first of all, we need to say which type of bond is homolytic fission actually occurring in. So you've got a covalent bond breaking. Then where do the electrons go? One electron goes to each atom. And what does that form? Radical substitution, so forming 2 radicals. And that is more than enough for 2 marks. You've got there the type of bond that's breaking, that's important for 1 mark, and then where the electrons go. It doesn't actually necessarily matter that you put forming 2 radicals, but that's what they do form, so put it anyway. Then moving over the page to our final question in this part 1, we've got butane undergoes incomplete combustion. Write an equation for incomplete combustion. So incomplete combustion, you get carbon monoxide and water. So here C4H10 plus, leaving a space, O2, gives me carbon monoxide, again leaving a space for balancing, plus H2O. So balancing the carbons first, we've got 4, so we must have 4 carbon monoxide, which now I need 10 hydrogens on this side, so 5 H2O. Counting up the oxygens now I've got on this side, so that's 4 there, 5 there, which gives me a total of 9. So I want 9 on this side. I've got them in groups of 2, so 9 over 2 will give me my balanced equation. There is a possibility on this type of question that they could throw in something like incomplete combustion, but forming soot. So could you write an equation for just the formation of soot rather than carbon monoxide? Soot being just carbon. So if they did something like that to you, in this case, let's get my pen back, you'd have C4. I shouldn't have done this extra bit, should I? C4H10 plus O2 gives you, this time, just carbon plus water. So if they said it was just producing soot, you just put C in your equation, and then you'd go ahead and balance. I've got 4 carbons, I've still got my 5 hydrogens. This time I've only got 5 oxygens here, so this will be balanced as 5 over 2 because I've got O2 there. So if they asked you to balance one with soot being produced, then you just put carbon there. Question 2, all about phosphoric acid. A short question, only 7 marks, with quite a cheeky little part C, where you lose your marks if you don't get the first mark right. So let's have a look at this one. First of all, they're basically asking for for you to define the enthalpy of formation. So they're giving you these 2 equations, and it says explain why delta H1. So explain why delta H1 represents the enthalpy change of formation of P4O10. So this is a test. Do you know your enthalpy of formation definition? Here, P4O10, notice how many moles you're making. So we've got here it is the enthalpy change when, spell my enthalpy right, shall I? Enthalpy change when, or rather, enthalpy change to form 1 mole of P4O10. I apologise about not having subscripts there. From what? Check. Is it from its elements? It is. We've got phosphorus and we've got oxygen there. So it's the enthalpy change to form 1 mole of P4O10 from its elements. So they're testing for that definition in a very specific way. They want you to talk about the formation and that equation, formation of P4O10. Then we've got a beautiful enthalpy calculation here. Enthalpy change of formation are shown in the table below. Calculate the enthalpy change of reaction delta H2. So delta H2 is this reaction here. Then, as if by magic, a very scruffily written equation appears on your screen. Here then I've taken down from the top of the page the equation. This is going to be the main equation in my cycle. I'm looking to work out delta H2, which is the enthalpy change along this arrow here. I've been given in my table formation enthalpies. So at the bottom of my cycle, I need to put, here we go, I need to put my elements down here. And then I'll draw my lines upwards. So let's just see if it will play. I can have my pen back. So I've got P4 plus, I've got hydrogen as another element, plus I must have oxygen too, O2. Now, it's going to be a bit of a guessing game since I lost my cursor, but arrows, yeah, that's a good start, isn't it? Arrows going up from the elements to the different components of the equation. Each one of these is represented by a particular value. So P4010 has got a value here. Stick that in there. So we've got P4010 here as being minus 2984. I've got 1 mole of it, so that stays as is. Then I've got, again, my water, which has got a value of minus 286, but I've got to times that, because the 6 moles of it, by 6, because that enthalpy change, remember, is the enthalpy change formation of 1 mole, sometimes that by 6. Then I've got here my phosphoric acid. I've got minus 1267. Here I'm making, or I'm producing 4 moles, so times by 4. Then I've got to look at the way I go around my cycle. So here I am. I'm going, if this cursor will let me do it, I'm going backwards down these arrows. So I have to reverse the sign of each of these. I've lost my cursor again. I've got to reverse this sign because I'm coming down that arrow, and I've got to reverse that sign. That sign stays the same. So my calculation overall will be, in here, no, don't crash now, that's really annoying. Okay, after some slight technical hitches, we should have delta H2 is equal to changing the sign here, so plus, oh, and here we go, it won't write me a plus, go on, why won't you let me write me a plus?